Mhm.
All right, I think I'm working now. I think it's all good. Hello,
Okay.
everyone. Can everyone hear me?
Yes, we can hear you.
Awesome. Great. Thank you so much. I apologize for the wait. I had some technical difficulties as I'm using a new computer now to join you guys from Washington, D.C., actually. So first and foremost, guys, thank you so much. If you guys have any issues with hearing my voice, just let me know and I can talk a little louder. Just to introduce myself, my name is Ricky Young. I serve as an engineer.
Sorry, we can
Yes.
we can see your screen. Are you showing?
Yes, let me share my screen. So here you go. Can you guys see my screen now?
Yes, we can see.
Okay, great. So I'm going to share my screen. And I want to again say thank you guys for inviting me. This is super cool. I've been well involved in various projects with Alberto, and I thank him for inviting me to this. For today, I'm going to go over using QBraid and doing a little quick introduction to quantum machine learning using PennyLane and our QBraid SDK. So I'm not entirely familiar with what the expertise of everyone here is. So if this might be a little bit easier for people, just consider this as if you have a machine learning background and you want a hello world experience to QML, that this is like kind of the way to get started here. And first and foremost, what's great is I'm going to walk you guys through how to make a QBraid account. And QBraid is a really easy way to get started on coding with quantum computers. One of the things we do, we offer Qiskit, PennyLane, Cirq, Rigetti, Pascal, and all these various quantum devices, as well as frameworks available out of the box with no installation necessary. So without further ado, I'd like everyone to make an account with us. This is going to be the very beginning. So you can go to account.qbraid.com and make an account. I suggest making a Google account. We will provide credits through this program. This will be interactive where you'll get to get familiar with QBraid and learn a lot more about quantum computing through various tools that we have as well. And we'll provide credits for this demo as well. Once you guys have made an account, hi Hitesh, hello. If you guys have any issues, just let me know. Make an account. And once you have logged in, if you use an email and password, you will need to register your email and then just make sure you confirm it. And if you use Google, you don't have to do that. So I recommend using Gmail. It's a little faster. So once you guys are good, just give me the thumbs up sign and then we'll keep going. So I can kind of get a gauge of where we're at. And while you guys do that, you guys should see once you log in a dashboard, which we will have all your quantum jobs. So all the jobs that you run on various quantum devices, as well as a course that's been approved by the White House Q12 initiative, which you can access here. And recently, I'd just like to plug that we had our hackathon, which was part of several quantum machine learning tasks, as well as some other tasks provided by QSF and QSteam, and various challenges were provided as well. And we have many speakers. So next year, if you're interested in quantum computing hackathons, please join us. We're everywhere. We're at MIT. We're also going to be participating in Xanity's hackathon as well. All right. So there's a lot of ground to cover today. So I'm going to go a little bit quickly. So first off, once you have done the adding your account, we're going to provide you guys a special credit here where you'll be able to get credits to access and run jobs on quantum computers. So this will let you run at least 10 jobs of small circuits for free on our quantum computers. And we provide quantum computers through IBM, AWS, and we'll be providing more quantum computers in the new year as well. So stay tuned. All right. So once you have created an account, or if you have an account already, I'd like you to access this GitHub. It should be publicly available. And let me see where my commenting button is. It's gone now. I'm going to, oh, there we go. So access this GitHub repository. And once you click the launch on QBraid button, it will automatically clone this repository into your account. So once you've done that, you should be able to see a repository similar to this here. with various portions of the presentation presented as well. And let me actually commit my changes. So let me save them as well. And once you have done so, you should be able to see various parts of this notebook. I'm going to assume you guys have gotten here. Again, once again, we'll be working on embedding classical images into quantum registers. And first off, you've made your account. You've added the code EHNU6626. You've clicked the launch on Kubernetes button, and now you should be able to open up the repository in this as well. So let me make sure that I have my final pushes just for you guys. That should push correctly. That's okay. So you should be able to see the QML embedding repository in your folder, in your file system as well. And we'll be first going through this embedding presentation that I'm going through right now. All right, does anyone have any questions so far? All right, I'm just gonna assume that's a yes. So once you have done so, on this side, you should see a QBraid SDK environment when you click add after you click EMS. And all you want to do is just install. So what you should see is right here. You should be able to browse environments and see the install portion right here. So you want to install it. For this, I'm going to install Pulsar because it's a relatively small package. But for our purposes, please install the QBraid SDK. The QBraid SDK allows you to transpile from various frameworks. So from Google's Cirq, Rigetti's Pikewheel, and various other quantum computing structures, frameworks, you'll be able to write a circuit in one and then transpile it and then send jobs to various quantum computers. If you'd like to learn more, we have docs as well, and you can read about them more here. And I will add it to the README as well. All right. So with that said, once it's been installed, you should see it on your left side here. I'm going to, and just make sure to activate it. So make sure to activate the QBraid SDK. And then you should be able to then make sure to activate the QBraid SDK kernel as well. So once you've activated the kernel, you should now be able to have various quantum computing packages that are all available through the QBraid SDK without ever installing through pip or conda. None of those things are necessary. They're all here and you can check all of them, and we'll even provide updates. So every time there's an update, we'll notify you and you get to quickly update without any of the hassle of dependency issues. So again, make sure to click your QBraid SDK, and we're going to get started by first installing TensorFlow, TensorBoard, and scikit-plot. These are necessary and not pre-installed, but with the magic command, you'll be able to install them into the proper environment. So once we've installed that, we're going to then delve into make sure that we also import all of the necessary packages. In this case, we also want to set our environment variable here. It's the same for everyone. This is where your QBraid SDK lives, and the TensorBoard that we just installed will be here. You may need to restart your kernel, but for this example, we won't have to. All right, so next, once you've run this cell, you should be able to then go to this cell. And how many of you guys are familiar with MNIST? Like, is everyone kind of familiar with it? Can I get a raise of hands or like just a bit of a feedback? Me, yes, Maha, awesome, great. So if you're familiar with MNIST, this should be basically it's like a seminal data set provided by, I think, UCI, some California and University of California College, where they provide essentially data sets that you can use for benchmarking and understanding some of the quantum algorithms. And for this case, we're going to be using MNIST with handwritten data sets that are originally 28 by 28 as well. And actually, I think it's 60,000 images that we'll be using. So if you are not familiar with MNIST, I'm going to go through a quick classical implementation so you can kind of get familiar with it if you aren't. So with that said, we're going to then normalize these images. They were from 0 to 255 scale down to 0 to 1. We have our training examples in our test set, and then we're going to one-hot encode. So what one-hot encoding means is essentially the test Y train, if you take a look at it, are actually the numbers that are represented here. So these are the images, and then this is the numbers themselves. So we're going to one-hot encode them, which means that we're going to expand this to be representing, we're going to use a vector of 10 zeros, where it will only be 1 if it's the correct index for the handwritten, which corresponds to the digit that's handwritten. So if it's 5, it would be 0, 0, 0, 0, 1, and then the rest of them would be 0 for the index. All right, does that make sense? So that's just one-hot encoding. That's a pretty standard technique that's used in machine learning. And as we plot it here, we can tell that these are the images here, 5, 0, 4, 1, 9. These are what we will be using a classical classifier as well as a quantum machine learning classifier as well. So when we run a convolutional neural network, what's happening here is that we're using this filter to extract certain features. This is very similar, perhaps, to like a Fourier transform in terms of how these are both integral transformations. And the equations are different, but you can maybe generally think that these are both similar techniques of extracting portions of an image using some kind of pass as well. With that said, we're going to also include some data tracking that you can use later on if you're interested to use TensorBoard. We're going to make sure that those are available. And we're going to build a classical convolutional 2D classical convolutional neural network here. We're going to have 2 convolutional layers. This is very much a simple example. And what we see here is that this actually has around 1.2 million parameters. And most of them actually come from the dense layer as well as this convolutional layer. And you can learn more about the classical part, but what I'm going to do is just keep going here. And it does take a little while for it to train. So I've already trained it for you guys in this case. And what we see here is that the model that we see here is going to train to almost perfect. You can check the accuracy here, check the accuracy, and it's already around 99 after only 5 epochs. So that's very, very good. This is like the current classical performance that we expect right now, that we hope that maybe quantum computing could have better performances, but there's still much work that needs to be done. Is anyone following along by doing the notebook as well? If not, that's okay, but would love to know. Anyone? Raise your hands. All right. Okay, so just going to do a quick analysis of the classical layers. What we see here is when you use the model, we're going to just make a quick confusion matrix, and you can tell that most of these are going to be correct. The 9s that are classified in this data set are classified as 9s. Most of the 1s are also classified as 1s. There may be a few areas here where it's misclassifying 6s and 0s, which might make sense actually. So I will get into that later, where people's handwriting can also be very bad, and that might also be a contributing factor. So let's see how a quantum machine learning model stacks up. So we're going to be using something called a parameterized quantum circuit, where we're going to use gates that are either, these are unitary operators, which consist of fixed and trained. So you can either train them, or they're going to be fixed, as in you can't train the weights that are associated with them. And in this case, what these weights are rotations of the qubits. And this is usually the standard implementation of a parameterized quantum machine learning algorithms, which are usually hybrid in the sense that the learning portion or the optimization portion is completely classical. And you also may have like an output that is a classical layer as well. So I'm just going to scroll back up. And you can tell here that once again, the classical data set is then classically preprocessed. We will go into the data embedding portion and just kind of delve into this portion as well today. And then you pass into a certain ansatz, you make the measurements, and then you provide an output. And then this part is just the classical optimization. So you may be familiar with like atom optimizers and various machine learning optimizers, but that's where if you have a machine learning background, this part should be fairly familiar. And this part, which is why I think it's a great way to kind of get started if you have that kind of background. All right. With that said, right now, and there's been some significantly great progress since I think like 2020-ish, when there was a binary classifier that classified 3s and 6s by Farhi et al., which I think did around like 85%, but now we're doing very, very well, where we're moving on towards not only classifying 4s and binary classifications, but we're also doing like multi-classifications and achieving some strong results as well. And you guys can take a look at these. There's been some results with the IRIS data set, which is a lot more friendlier than the MNIST data set as well. That's achieving 92%. And I think there are some great results that I haven't caught up with, but the last time I checked, some of the really astounding ones were around the 85 to 90% range for a 10-class classification. So there's some theoretical benefits, but I do want to say, like, there's a lot of buzzwords here, like machine learning and quantum computing, but we have to understand that there's a lot of, I want to make sure that everyone's clear that the quantum machine learning portion of this actually has a lot of thinking and a lot of great research needs to be done to make it actually beneficial, because of the fact that it's just so new and it's still such an active area of research that you are going to just have to just answer a lot of these questions and even ask what questions are the right way to ask as well. Again, so I really want to stress that this notebook is not supposed to hype up everything. Yes, absolutely, Hitesh. I can definitely do that after this. And in fact, I think tomorrow, I was actually hoping that this was going to be a talk that was after Catalina's, but if I'm correct, Catalina will be speaking tomorrow and she'll be doing a tutorial on Penny Lane. And I actually recommend that as well. So some of the frameworks that we're going to be using today are going to be using Penny Lane. So with that said, what we're going to do right now is we're going to, so yes, Hitesh, I will send you some resources here, but I personally found, my introduction to ML was MNIST, and it would be nice to do a QML introduction using MNIST, and we'll go from there. So some of the theoretical benefits, there's some time complexities that might be improved over time because of some linear algebra subroutines using kernel methods. Right now, we're using parameterized quantum circuits that are not kernel methods, but essentially, if you think about it, a Hamiltonian, essentially quantum mechanics is just linear algebra, or it must follow linearity, and therefore there might be some benefits to using quantum computing for linear algebra subroutines. Another one is, we may also expect exponential time complexity speedups, but I think the best way of taking an understanding of QML right now is that there needs to be better ways of framing the problem and understanding it correctly. If you have any questions with regard to this, I actually really like this post by one of the leaders in this industry or in this research field, Maria Schold, and she's actually works at Penny Lane. And she just kind of answered that as well here. And that's where you can learn more about it too from that link. All right. So some of the challenges there are that require further research is that there's an embedding and decoding classical data using quantum circuits is hard. There's everything from there doesn't exist really a QRAM, that's a quantum random access memory, to even store the data. So not right now, what I'm going to present to you is like embedding methods to store data. But even then, it's actually considerably challenging to accurately use quantum computers for embedding quantum classical data. But there's a lot more promise to using quantum data for quantum machine learning tasks, for example. That is kind of where perhaps like Richard Feynman's original thought was, is you want to use a quantum computer essentially because using a quantum computer should probably be more helpful compared to, for example, using classical computer to use quantum computers. And this kind of goes vice versa. But we're hoping that, given that parts of machine learning do use linear algebra, that it might be useful in some cases. Yes, and then there's some just hardware issues. There aren't enough qubits. Existing qubits are prone to error. So this is where, a lot of the hardware right now, although there's been immense progress where IBM has released their 433 qubit quantum computer. And there's some great startups that are doing great work as well, including Quandela, Pascal, and QEra recently has joined AWS in providing the cold atom quantum computers. This is where we still need to get better quantum computers that can achieve performances that can actually do genuinely reasonable amounts of work when you are training, for example. Essentially, it's like your tires are kind of broken, so or they're kind of shabby tires, so your car might not even run in the first place on them. So we want to have good qubits. Yes. And then there's also the cost of running qubits, of running variational algorithms, which can be fairly expensive. And this is very much the same for QML. You can expect that even on an IonQ device, it would cost around 3 to 4K. And, even if you are going to run, QBRate does provide credits very generously, as well as AWS, IBM, of course. And what's great about QBRate is you actually get both of them all in one platform, and that's one of our selling points as well. But again, they do also a great job, and they have great support structure as well. So I would recommend getting credits. And there's also a whole host of other issues as well, but I would probably perhaps say that these are challenges, and they should be exciting challenges, whether you're in the hardware side, you're in the business side, you're in the engineering side. These are all things that we need to do, and we need to just go tackle and have fun tackling them to make quantum computing useful and make it better and better. Yes. Overall, there's even questions of like, how do you apply nonlinearities, which is also a fun problem. So I recommend just kind of digging into it on using various resources, which I'll send later. All right, so we're going to pre-process the MNIST data set. And this is where the reason why we need to pre-process it is because you can only use so many quantum qubits. And since we only have so many qubits available, what's going to happen here is that we have only, for example, in this demo, I wanted to try to limit it to 8 qubits. But most certainly, this classical pre-processing portion is actually very important. And you can do a lot of customization here to make sure that it works very, very well. So with that said, we're going to today look at angle embedding as well as amplitude embedding, which are two of the most seminal methods of embedding, and you're going to see how easy it is using PennyLane as well. And yes, so for angle embedding, you want to actually remove this 5-pixel border around the image. So I'm going to scroll back up. You see here, there's like this purple border here. For most of these images, they won't get cut off, right? So we actually want to just remove that. And then we can also then resize the image to 8x4. Secondly, for the amplitude embedding, we will also remove the 5-pixel border and then resize the image to 16x16. Already you can tell that probably the amplitude embedding is going to be perform a little bit better because of the fact that you have more pixels and you're expressing this a little bit better than, say, the angle embedding. But no matter, again, this is just a demo. This is where, if you want to delve in, get into this from a researchy perspective as well, this is where it's quite fun, I guess, just to like think about how to best express various data sets and to make that a generalizable for certain embedding techniques as well. All right, so I haven't been running things, but I think we should be okay. I'm just going to clear this up. Clear output. Okay. So first off, we're going to then we're going to crop both of these images. Again, so the test set and the training set are going to be cropped. And just to clarify, we use a training set to train the data, and then we use a test set to test whether we have made sure that we haven't underfit or overfit the data that we trained on. So then we're going to add another dimension, so then the resizing works smoothly. And then what we do is we're going to then resize it for angle embedding. So this should be 8 by 8. Sorry, that is my fault. Let me just change that to 8 by 8. And then what we're going to do is also resize it to 16 by 16. So then what you get is for angle embedding, we get a 16 by 16 image. And then for it should be an 8 by 8 image. And then we should get a we should get something very similar for the amplitude embedding. It should be 16 by 16. So we can just check these images as well. We get something like this for our 256 image, which is our 256 is our 16 by 16. And then we also get a 8 by 8. So this is actually a 64 pixel image here of 7. They kind of look similar, but again, like what happens is when you actually run this through a parameterized quantum circuit, it usually does better with more data, which makes sense. One more thing is that, when you downsample these images, what happens ultimately is that it can get really scrunched up. In fact, people also just have bad handwriting. This is classified as a 5, I think, or no, this is classified as a 3. But since the 3 portion is so scrunched up here, it actually looks like a 5. So you can't blame that even, the best models can always get a few things wrong. So this is the classical confusion matrix for a 0 and a 6. It makes a little bit of sense that people are, the model might get it wrong, because sometimes people might draw these 6 and then just draw to the top very closely. So I can actually, so I'm going to just draw quickly here. Do I have the ability to draw? I'm just going to use a whiteboard. So I'm just going to quickly, so just this verse, say this is your 0. I wouldn't blame myself if I got this wrong as well. So that's just kind of some of the things that when you use like a quantum machine learning model, it actually gets a lot worse. So, but people have been working on this a lot, and it's actually gotten a lot better as well, since people have been trying to solve better ways of making this picture better looking, roughly said. All right, so we're going to use Penny Lane. So in Penny Lane, the qubits are called wires or registers, and we have like certain weights and shapes to these weights as well for training on them as well. So the first one, as mentioned, is angle embedding. So for each qubit, don't know if you guys, for each qubit, you get to actually rotate the qubits. And what we do is, according to the pixel values here, we're going to rotate it by the poly Z operation. So gate operation. So we're going to, for every nth of I, so this n, and you can assume is just like the vector of every row of images. So let me pull up the whiteboard again. So let me clean this up. Right. All right. Let me clean this up. So you can assume that when you are using the image, when you're classifying, or when you are kind of embedding this image, you have this big image here, and every n is just this row, and then every I is right here, And then we go dot, 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 dot. And then we do ends of n-1 here at the very end. So we're going to encode all of these as rotations here. So on every quantum register that we see, since we have an 8x8 image, so it's an 8x8, every single pixel here that we have, we will encode as a rotation of in the z direct, z rotation, as a rotation around the z-axis by the n sub I amount. So yep, that's what we're doing here. Going to share back. That is essentially angle encoding, and you can learn more about this through various resources. And so let me make sure I run all my cells. Run this one, right? And then we have our QML device here. And what happens is when you actually run this angle embedding, we actually get something that looks like this. So we have, this is the first row, second row, third row, fourth row, fifth, sixth, seventh, eighth row. So these are all your rows that we just showed in the whiteboard, and they are now just encoded in this fashion here for encoding. This is fairly excessive. I would say that there's probably a lot of optimization you can do. And the reason why I say that is because, or you can actually reduce the image size as well. That's, I think, what I originally did was an 8x4, so you didn't have so much of so many pixels to encode. But I ultimately thought, you know, this is just a demonstration. I think it's better to just do something where it uses 8x8. And then finally, we also have to read the expectation values of this circuit after it passes through the trainable layer. And what that means is you have to actually make a measurement at the end to understand what the results were from passing through this layer. And what we have used is the Zhang et al. All-qubit multi-measurement multi-measurement readout strategy, where we're going to make a measurement of poly X, Y, and Z on every single qubit here. So, and by doing so, we actually end up basically being able to get the best, well, get the best results if you assume to run the full model. It does take a long time, so I'm just going to save time and not run it. But this is probably helps a lot compared to just like a single readout strategy like this, or other readout strategies. It seems to perform far better than the other ones as well, in terms of providing some kind of nonlinearity at the end of applying your quantum layer. So we're going to use the strongly entangling layers, which are just like a quantum central circuit classifier layer, circuit template for our weights, and our weights are the parameters that get trained in this case. So we run this. We turn it into a Keras layer, which is the TensorFlow interface for quantum machine learning. And we make this a sequential model. We compile it with the correct shape. We run the model. And then this part takes an incredibly long time. So in your free time, feel free to run it. I'll provide you even more CPU resources if you'd like. And we actually achieved something around 65%. With only 5 epochs and a very limited data set. So hopefully, once you do run it, you'll be able to see that there's a lot of work that needs to be done. But one of the seminal strategies for embedding is to use this angle embedding strategy as well. All right, how am I on time? Okay, so I probably need to go a little bit faster. So with this amplitude embedding strategy as well, we will be running, this essentially encodes it in the amplitude of each of the circuits, the states that are provided by the qubits. And so if you use 2 qubits, you actually have 4 states that are possible. And so you can actually encode 2 to the n features. So this is actually why you can do 16 by 16 images here. And this is kind of how it looks like. When you run this model, you actually get somewhere around 48% after running it on 2 epochs. And this actually also goes up to around 5%. But in the interest of time, I will skip this because I have not taken the time to finish it. And there seems to be a keyboard error as well. Later, I'll just like run the whole thing just to show you guys what it does ultimately. And you can check it through the GitHub link that I sent. But when you look at some of these results, so the Zheng et al. That I mentioned does 89%. Alberto and I worked on one that also works to about 85%, but uses only 10 qubits. And we also use much less parameters. So the 93,000 is perhaps another convolutional or just like a simple neural network. So this is actually kind of the results that you would get after running it for many, many epochs. But again, this is just to demonstrate the results here. And if you do run a fair model, for example, which is just like a regular model, it essentially should be able to perform fairly well and get around 82 to 83%. So let me just make sure to just run this cell. So let me run the Y train from hot model. So I'm just going to Y hot encode it. Go back here. Yes, another thing is it does take a while unless you like parallelize and do some fancy techniques for making sure that the model actually runs. So yes, those are things that we also need to work on. I'm going to just run this. And so we have a very simple, easy model, and it achieves around 75% to 78%. Of course, it wasn't trained fully, but you can assume that there's a lot more potential even just for a fair model, which actually has, even then, it has around 2,570 parameters, which is a lot of parameters compared to the quantum models, which had a lot less. All right. Finally, I just want to run through the QBraid SDK. So with the QBraid SDK, you can take a penny lane function like the angle embedding that I mentioned. And say, for example, you learn Qiskit, but you want to use penny lane. You can actually write this circuit once and then be able to transpile it from various languages that are available. So Circ, PyQuil, Qiskit, Brocket, penny lane. So I'm going to change the penny lane circuit to Brocket, then change it into a Google circuit, then a Qiskit circuit, which is the IBM, and then back into a PyQuil, which is a Rigetti circuit. And then finally, I can just change it back to a PyQuil circuit as well, and into a penny lane circuit as well. I think I'm just barely on time. Sorry, I couldn't run these models. I was just in the midst of doing that and I couldn't quite get it done, but I will post these once they're finished out in the GitHub, and then you guys can reference this as well. All right. Any questions? And I will send links in terms of just resources as well, and put it in the GitHub as well. Yes.
También si gustan pueden escribir sus preguntas en español, si da pena preguntar en inglés.
Could you repeat that question?
No, I was talking with the participants. I told them that they can write their answers in Spanish if they have problems with English. But there is a new question in the chat. How many qubits can be used in QBraid to implement an application?
That's a great question. So QBraid actually is not a hardware provider. We provide the platform for you to code on quantum computers. So what's great here is I can show you one of our demos that you can also clone into your QBraid repository as well. And I can show you some of the devices we have available. So here you go. You can check out this demo and you can clone it into your QBraid account. And let me share my screen just to show you what kind of devices we have available. So I'm going to go to QBraid Quantum Jobs. In this demo, you can see that we have, not this one, SDK devices. We have simulators, annealers, IonQ, IBM, and various other Oxford quantum circuits. We'll have Cura, we have Xanadu now. We'll have Pascal and a few other quantum computers from a few other providers as well. So you can actually access all of these. You can query for them, check their status, all through your notebook. You don't have to go to another site or anything. And you can make one circuit, for example, in Qiskit. And then you can transpile it as I did before for a Google device, and then just run the circuit actually. And then you can actually see all your jobs. So what's really great is you can write your circuit in any framework you want, and then just submit it to any of these devices except D-Wave because they're an annealer. And you can verify that your results are going to be the same as well. Yeah, you're welcome, Max. May XX. Yes. Wow, that's a great question. We will actually give you credits if you find, you should join our Discord, which funny enough, Alberto is our community guide as well for our Discord. I recommend joining it because you can get more credits by finding like bugs. We have a bug bounty program, and we also have various other fun ways, such as if you are in the QSF mentorship program, you are provided credits as well for just joining our, just using QRaid and running devices for your project. So that's something that maybe Alberto might be want to talk about, or do you guys know about QSF? It's a really great program. No. Oh, okay. So you guys have to check out QSF.org. I think that's correct. But we provide credits for any individuals who are in the mentorship program. If you do a hackathon, we're going to do the next one at MIT. It's virtual as well, so you can attend. You should definitely do these things. These are where you get programs, and then join our Discord community as well. So let me share the link to that. And you can then kind of get started in joining this quantum community. We're super active, and we are at almost every hackathon. So if you want to code and get better at quantum computing, I recommend just doing these challenges, getting some cool prizes along the way, and meeting some cool people from the industry, from research, and also just participating is super fun. I did a few of them myself, and they're always a blast. So I recommend those two things. So MIT as well as the Quantum Open Source Foundation are great places to start. QSF.org. Any other questions? Oh, and you should also ask Alberto. He's like an expert in all these things too. So. Thank you as well. This was a lot of fun. I apologize for the late start. I'm getting a hang of using my new computer now. So.
Thank you so much, Ricky. Don't worry for the delay. Well, that's all for this talk. And well, in 10 minutes, we'll start the last talk of this day. So thank you so much.